isn't it annoying when your voice assistant misunderstands you, like not for what you were saying, but just for how you said it? Yeah, absolutely. It's very annoying. While it may sound like a small glitch, but that problem highlights a much deeper issue in ASR systems, and resolving that issue, or at least mitigating that issue, is the main focus of this thesis. With that in mind, I am Mehdi Hassan Vijay, and I am presenting my master's thesis on multi-teacher knowledge distillation for accented English speech recognition. And this research was conducted as a part of my studies at Aalto University under the supervision of Professor Mikko. Yeah. And here's the structure of the presentation. So I will begin with a brief introduction. Then I will highlight the research gaps and questions that motivated this study. And then I will explain the proposed multi-teacher knowledge distillation method, and followed by its empirical outcomes and error analysis. And I will also briefly touch on how this proposed approach can go beyond accented ASR by validating its efficacy for speech emotion recognition. Then I will share some findings and insights, and that will naturally lead us to the discussion on challenges, open questions, and future directions. And I will wrap things up with a conclusion. Okay. So first thing first, why do accents matter in speech recognition? Well, English is a global language and it is spoken in many different ways. In fact, over 1 billion people speak English as a second language, uh, which is nearly 3 times the number of native speakers. That means a substantial amount of spoken English is accented, and these accents affect pronunciation, rhythm, and prosody, which are the main differences that ASR systems need to handle effectively. Uh, However, most of the ASR systems are mainly trained on mainstream accents like British or American accents, and this limited exposure make them poorly equipped to handle the diversity found in the real world speech. So they often fail when faced with non-canonical accents, and this problem goes much deeper since these approaches lack the mechanism for accent-invariant feature learning, which are essential to address out-of-distribution accents. And when we try to fine-tune the models on new accents, we run into catastrophic forgetting, which is another pivotal issue. So all these factors together create a major bottleneck to develop a robust ASR system. And uh, this slide, this slide highlights the research current approaches that are tackling accented speech recognition and highlights their key limitations. As you can see, while these approaches are trying to solve one problem, they introduce another. For instance, approaches like accent-specific fine-tuning, domain adaptation, and ensemble techniques suffer from high computational overhead and poor zero-shot generalization. Even advanced approaches like meta-learning and multitask learning are still suffering from rigid supervision and they lack sequential adaptation capacity. What puts our proposed multi-teacher knowledge distillation effort is its capability to address all of these limitations. And most importantly, it results in a unified student model that works well for both seen and unseen accents, something that all the previous approaches failed to achieve. So here are the 3 research questions that I focused on during this study. The first research question is, does multi-teacher knowledge distillation facilitate the learning of more robust and accent-invariant acoustic representation than accent-aware fine-tuning? Second, how does teacher ensemble heterogeneity influence the robustness of multi-teacher distilled student in zero-shot scenarios? And third, to what extent does multi-teacher knowledge distillation mitigate catastrophic forgetting compared to fine-tuning when progressively adding new accents? And here is the proposed dual adaptive multi-teacher knowledge distillation framework. So it comprises 10 accent specialist teachers along with a student model, a neural teacher mixture, and a meta-learned objective adapter. So at the top, there are 10 accent specialist teacher models, and each of these teacher models are fine-tuned on one particular accents, and these models are labeled as T1 to T10 respectively. The student model is at the bottom, which is denoted as S, and each of these models basically share a similar architecture, which comprises a temporal compression module followed by a context modeling network. In fact, these models are built on top of wave-to-vector based foundation model. However, to creatively or intelligently combine the teacher's knowledge, we introduce a neural teacher mixture. So it dynamically weights each of the teachers' contribution based on their distillation losses and results in weighted distillation loss. And this weighted distillation loss is further goes through the meta-learned objective adapter that adaptively balances between the distillation loss and alignment loss. So let's dive deep into how multi-teacher knowledge distillation actually works. So we have the raw audio waveform, which is fed to each of the models. So each of the 10 teacher models and the student model, and each of these models process that raw audio waveform and produce logits. And then these logits are further used to calculate the distillation losses and alignment loss. So to calculate the individual distillation losses, we compare each of the teacher's logits to the student's logits, and we are getting the distillation loss. And then we utilize the student's logits to get the alignment loss. Now, the individual distillation losses are further goes to the neural teacher mixer that dynamically weights each of the teacher's contribution, and it returns us the weighted distillation loss. And now that we have the weighted distillation loss and alignment loss, so these two losses goes through the meta-learned objective adapter that adaptively balances between these two loss and return as the total loss. So all of these things are happening in the training phase where teacher models are kept frozen. That means during the back propagation, the student model along with neural teacher mixture and meta-learned objective adapter updates jointly. However, during the inference, we utilize only the student model. So the student's logits are passed to the CTC decoding module that gives us the text output. Okay. So here's the training configuration. Each of the audio samples are resampled to 16 kilohertz while keeping a vocabulary size of 32. And temporal compression was achieved using a 7-layer convolutional encoder. There was a linear projection layer that project 512 dimensional vectors to 768 dimensional vectors, and then the context modeling incorporate 12 transformer encoder layers. So each of these models were trained for 20 epochs using Adam with weight decay optimizer while keeping a batch size of 16 and a learning rate of 0.0001. And throughout the training, the linear learning rate scheduler was employed. And we utilized 4 data sets, so accent 200 hours and EDEC development. These 2 data sets were mainly used for training the models. Accent 200 hours comprises 200 hours of data from 10 English accents, and we considered these 10 English accents as seen accents. And then EDEC development set that comprises 16 hours of data from 24 accent categories, and we considered these 24 accent categories as unseen accents. For benchmarking, we utilize 2 standard benchmark test set, which are accent 20 hours and EDEC test set. So the accent 20 hours comprises 20 hours of data from those 10 seen accents, but without explicit accent levels. And then EDEC test set includes 17 hours of data from those 24 unseen accents. And this was considered as the held out set or out of distribution test set. Yep. And the model performance was evaluated using word error rate and character error rate. For the baseline, we have 3 baselines. The first one is FT, that indicates standard accent specific fine tuning. And then for MTKD top 1, where only the most aligned teacher selected by the neural teacher mixer is used. And MTKD rank weighted, where teachers are ranked by their distillation losses and weighted accordingly. Now the focus shifts to pre-trained model selection for cross-accented ASR. So the task involved fine-tuning the model on American subset of the data and then evaluating it on those 10 seen accents along with the standard accent 20-hour benchmark test set. So 4 wave-to-vector base pre-trained models were compared, and among these 4 models, wave-to-vector base 960-hour one gave the best performance. It achieved average quad error rate of 14.4%, which is a 12% relative improvement compared to the next best wave-to-vector base XLSR model. The empirical outcome shows that it balanced the trade-off between specialization and generalization. So basically, this particular one behaves like a general linguist by neutralizing accent variation while retaining performance. The lower character error rate also validates this information. And the next challenge was finding the right training scenario to fine-tune the model that balances generalization with retention. So 3 training scenarios were tested. So firstly, the models were fine-tuned on accent 200 hours data, and it performed well on seen accents, but failed to generalize to the unseen accents. And then the models are fine-tuned on EDEC development data. It adapts well, but forgets previously seen accents. So basically, it is raising the classic catastrophic forgetting issue. And then the models were fine-tuned on combined dataset, which gave the optimal trade-off by giving a strong seen performance while adapting well to the out-of-distribution accents. And now, if we look at the figure in the right, we can see fine-tuning the model on the combined dataset, it improved 9%, maybe, yeah. It improved approximately 9% word error rate while testing on the EDEC test set. And it also showed that some accents were getting more benefit than others. For instance, it improved 24% word error rate for Romanian, while only 17% for Indonesian. And another observation was that the same level does not necessarily indicate the same phonetics group, because Chinese appeared in both sets, but with significantly different phonetic patterns. Now let's discuss the meta-learned weighting strategies used in the proposed multi-teacher knowledge distillation methods. So 4 beta weighting configurations were tested. The first one is regularized configurations, where weights are meta-learned and softly constrained. The second one is CTC-only configuration, where the teacher's guidance is completely ignored. And then unregularized dynamics, which is still an adaptive learning strategy, but without any constraints. And then the KL-only setup, where the system solely focused on the teacher supervision, and it didn't work at all. So it failed completely and always gave 100% word error rate. So focusing on beta CTC, it played a crucial role in preserving acoustic supervision, as shown in subfigure F. But CTC-only supervision, this setup hinders the generalization. On the other hand, beta KL collapse to 0 in unregularized setup, and when this happens, it tends to avoid or neglect the teacher supervision. So consequently, it leads to a weak teacher signal. But in contrast to this approach, when we solely focused on the teacher supervision, it didn't work at all. And finally, the regularized setup, which worked the best, and it ensured that the balanced reduction in all 3 losses, the CTC loss, scale divergence loss, and total losses, as shown in subfigure C, D, and E. And now let's compare the multi-teacher knowledge distillation across different accents. So 3 aggregation strategies were benchmarked. The first one is MTKD average, which utilizes uniform logit averaging, and then MTKD rank weighted, which is a rank-based weighting aggregation strategy, and then MTKD top 1, which selects the top aligned, best aligned teacher. So among these 3 aggregation strategies, the MTKD average consistently outperformed others, as shown in the table. It reduces systematic biases through ensemble smoothing, as it combines or averages multiple teachers' output. So it basically reduces one of the particular teachers' spike, and it also ensures balanced accent coverage by preserving minority accent cues. For instance, it achieved 4.9% word error rate improvement for Chinese, 4.4% for Japanese, and 3.5% for Russian. So it appeared that this setup also worked best with the regularized beta. So it gave the most robust results when we combined MTKD average with regularized beta setup. That means it generalizes better under phonetic variability and accent imbalance scenario. And here, let's compare multi-teacher knowledge distillation with fine-tuning on the standard test sets. So starting with the word error rate reduction, the figure explicitly showcases that multi-teacher knowledge distillation improves word error rate across both of the standard test sets. In fact, it improved a 5.26% relative improvement on the accent 20-hour benchmark test set, and the relative improvement was even better in EDEC test set, which is about 10.19%. So these improvements indicate that multi-teacher knowledge distillation offers better generalization across different accent variations, and in fact, it tends to work better in challenging scenarios, as the relative improvement was much higher than accent 20 hours data, which was basically our scene accent or in-domain data, but EDEC test set was our out-of-distribution data. And these results indicate that fine-tuning suffers from memorization, while multi-teacher knowledge distillation encourages phonetic interpolation. And the same setup now, let's test them on the zero-shot adaptation. So in this setup, all the models were trained on the American accented data only, and then evaluated them on the 24 diverse accent found in the EDEC test. And this setup really tests the model's ability in generalization, and this table validates the efficacy of multi-teacher knowledge distillation for generalization. So it achieved it improved the average word error rate, and again, it gave a 10.18% relative improvement for word error rate, and 13.18% relative improvement for average character error rate. And most importantly, multi-teacher knowledge distillation benefits all the accents, not just a few. And top gains were achieved for Italian, Kenyan, Israeli, Ghanaian, and Irish accented English. And why does multi-teacher knowledge distillation work better? Well, firstly, because of the multi-teacher setup that produces average logits, and then the balanced optimization technique through meta-learned loss adaptation that helps the model retain generalizable phonetic patterns. And both these approaches helps the model to overfit to one particular accent that is dominant. And now let's look at different error types that these models can make. So the figure shows that the substitution error is the most dominant one. So here the fine-tuned baseline produced about 245,000 substitution errors, while multi-teacher knowledge distillation reduced it to 31,000, which is over 14,000 substitution error reduction. And this improvement is significant as the substitution error dominate the total count. It reflects the improved phonetic level disambiguation. That means multi-teacher knowledge distillation has better phonetic understanding compared to fine-tuning. And it also improved the error count in deletion and insertion error, but this drop was modest compared to the substitution drop, but still it suggests the general fluency gain for multi-teacher knowledge distillation over fine-tuning. And the key takeaways from here is that multi-teacher knowledge distillation retains rare phonetic patterns without overfitting. And an easier way to think about this is fine-tuning is like it talks fast and listens less, while multi-teacher knowledge distillation listens carefully before speaking. And now let's discuss the temporal variability and how it is affected by different accents. This is an important aspect of accented ASR systems, which is often overlooked by existing approaches. So this figure shows the male spectrogram for the utterance, "Come and see me in my room this evening," which is spoken in American accented English. It highlights a difference model align and attend to the input features over time differently for different accent variations, even though the words are similar, but their temporal alignment is significantly different. So it indicates that different models handle different acoustic cues based on their accent conditions. and there is not really any universal phoneme timing. That means phoneme timing can be changed based on user accents or individual accents. And here we have three different specialist models. The first one is a specialist in American accented English. The second one is in Canadian, and third one is in Spanish. So even though each of these models predicted the transcript accurately, but their alignment is different, that indicates the models agree on what is said, but not when it is said. And here comes our multi-teacher knowledge distillation handy. So it preserved the temporal diversity across models as it averages multiple teachers' outputs. So consequently led to better generalization. Now let's extend the proposed multi-teacher knowledge distillation beyond accented ASR. So why multi-teacher knowledge distillation for speech emotion recognition? Because it focuses on paralinguistic cues instead of solely focusing on the words. And it makes it a good test, or in fact, the perfect test to analyze and see how well multi-teacher knowledge distillation capture raw acoustic representations. And in fact, emotions tend to be universal across languages that can reveal multi-teacher knowledge distillation's language agnostic power. So we propose two variants of multi-teacher knowledge distillation for monolingual and multilingual speech emotion recognition, and we compared these approaches with three more baselines, which are monolingual fine-tuning, multilingual fine-tuning, and monolingual knowledge distillation. And we tested these methods on three languages, which are English, Finnish, and French. And for English, we utilized IMOCAP data, and for Finnish, we utilized FESC dataset, and for French, we utilized the CAFI dataset. So here table 5 showcases the results of monolingual speech emotion recognition, while table 6 compares the results of multilingual speech emotion recognition. And looking at table 5, we can see the multilingual variant of multi-teacher knowledge distillation gives the best overall performance by achieving the highest mean weighted recall. And it also gives better generalization compared to other methods. So it achieved top weighted recall score in 4 out of 5 splits. And now looking at table 6, it showcases the superiority of multi-teacher knowledge distillation, as the monolingual variant of multi-teacher knowledge distillation outperformed the monolingual baselines, and the multilingual variant of the multi-teacher knowledge distillation outperformed the multilingual baseline on both English and Finnish dataset. But it didn't performed well on the CAFI dataset, which is justified as CAFI has only half an hour of data. So in each batch, the CAFI data remains the minority group. So during the multi-teacher knowledge distillation, it either choosing the English teacher or choosing the Finnish teacher. So consequently led to a lower performance for French data. And here, the figure illustrates that the multi-teacher knowledge distillation, the multilingual variant of the multi-teacher knowledge distillation significantly reduced the misclassification count. So the main findings are here. So our proposed multi-teacher knowledge distillation showcased superior performance across multiple benchmarks. It outperformed the strongest fine-tuned baseline. And it also showed a strong generalization to unseen and out of distribution accents. It improved error robustness, as there was a major drop in substitution errors. So it also validated that aggregation strategy matters. So we have seen that uniform averaging strategy gives the best balance in accent diversity. And then dynamic clause weighting is also crucial. And multi-teacher knowledge distillation is proved to be versatile across tasks, which is validated through speech emotion recognition in 3 languages. And now let's go through the research questions. So the first question was, does multi-teacher knowledge distillation facilitate the learning of more robust and accent-invariant acoustic representation than accent-over fine-tuning? The answer is yes. Multi-teacher knowledge distillation outperformed strongest fine-tuned baseline on both seen and unseen accents. And then how does teacher ensemble heterogeneity influence the robustness of multi-teacher knowledge distillation in zero-shot scenario? The empirical outcomes showed that it positively influenced. We have seen a greater teacher diversity led to better generalization. And finally, to what extent does multi-teacher knowledge distillation mitigate catastrophic forgetting compared to fine-tuning when progressively adding new accents? Well, it markedly improved catastrophic forgetting as the empirical outcome showcased that multi-teacher knowledge distillation preserved prior knowledge better than strongest fine-tuned baseline. And here are some challenges faced, open questions raised, and future directions worth exploring. So the first challenge is about learning accent representation without levels. So in reality, accent levels are often missing. So the open question is whether accent clusters can be merged without explicit levels. And a potential research direction could be using unsupervised learning to incorporate accent agnostic embeddings. And then another challenge was in temporal misalignment. So currently there's no time wrapping between the student and teacher fix, which often lead to misalign the supervision. So here's the question is, can we correct these misalignments without global attention? And one potential solution could be adding local attention to guide the frame level distillation. And then another challenge is in teacher selection strategy. So currently teachers are based on distillation losses. Teachers are selected based on distillation losses, not the alignment loss. And it was found that the best KL aligned teacher does not always necessarily result in the best transcription. So the question is, does lower character error rate can lead to better learning? And one potential future direction worth exploring is trying multiple or trying hybrid teacher selection strategy that can balance scale fit along with transcription errors. And another challenge was in shallow supervision, as currently teachers are distilling their knowledge from their logics. So they're basically doing logics level supervision. So there is no internal layer guidance in current multi-teacher knowledge distillation approach. So the open question is, can intermediate features improve distillation depth? And future research direction can extend this to a multi-layered distillation through attention maps. Okay, so to conclude, we propose a novel dual adaptive multi-teacher knowledge distillation framework for accented English speech recognition, which comprises 10 accent specialist teacher along with a student model. And the architecture also incorporate a neural teacher mixture and a meta-learned objective adapter. And then we extended this method beyond accented ASR by empirically validating its efficacy for speech emotion recognition, and that there in speech emotion recognition task, multi-teacher knowledge distillation achieved the state of the art performance in 3 languages. And to conclude, multi-teacher knowledge distillation emerged as one of the principal routes towards inclusive and resource-efficient speech technology. So that concludes the presentation. Now, thank you. Thanks for attending. Thanks for your time and attention. If anyone have any question, I would like to take them now. Or maybe later you can also send me an email here.
Yeah. I could ask about this training, since you have accent labels there in the training data, so you know which accent it is. Yes. Are you using these accent labels?
Yes, so we are using basically this to develop the specialist teacher models. So not during a distillation. So in order to create the specialist teachers, we train these teachers in using each of those accented data.
Yeah.
So
when you train the whole system?
No, we are not using
that. Just kind of matching, you had this top 1 teacher, so you basically selected the teacher that matched best. Yeah, so not using the label teacher. So it might happen that actually some teacher, usually probably the kind of accent specific teacher would be the best, but you are not using that knowledge anymore at that stage. Yeah, so for
during the inference, we are not really using any levels. So we take a random audio and we align it with the teachers using the distillation or KL divergence losses. So whatever the teacher is best aligned with this audio sample, we guide the student model through that teacher model.
Okay. So you have then, in this picture, you have 10 teacher models, right? How did you arrive at this number? Was it like based on the number of accents in the data?
Yeah, it was the number of accents available in accent 200 hours dataset.
So why don't you just use the teacher models?
So for teacher model, we need to know the level, like what is the accent of the audio sample beforehand. So,
but could you just select somehow the best teacher without knowing label?
Yeah, that could be
with some confidence measure or something.
That could be one way, but in that case, our main goal is to develop one unified model that can be capable of recognizing all 10 of these accents, not just one. So in your case, when we are testing just using the teacher model, so we need to keep all these 10 teacher models while testing. So when one audio sample is coming from X accent, then it is selecting one of the particular models. And then when another audio is coming from Y accent, then it is choosing another audio, another specialist teacher. So this is how it is giving the text output or predictions. But in the case of our student model, it is during the inference, it is keeping only this model. So this one model is capable of reproducing all the teachers' specialization. Yeah.
When you did the font tuning, did you do the, like, when you tested how the like base model accents, did you train those on like one specific accent or like a group of accents to see how it performs?
So the teacher models are fine-tuned on one particular accent.
No, I meant like you had the baseline test without the teacher models. So how did you conduct that?
Oh yeah, the fine-tuned baseline is on multiple accents.
Okay.
That was tested on different data sets, EDEC tests and accent 20 hours data. So the one data set has 10 accents, the another one has 24 accents. So in total, 34 accents.
What was the catastrophic forgetting that you observed in your case? Is it that model learned for a particular accent and then it would you fine-tune it for some other accent it would forget? What was it exactly that you observed in your case?
So that was the case. Okay, so here, so when we fine-tuned our model on the EDEC development data, so we have seen that it forgets the previously seen accent. So the wave-to-vector base one has trained on some English data also. So it is not for ASR task, but in general for pre-trained on some English data. So it has some knowledge on English speeches. So when we fine-tuned the model on EDEC development data, we have seen that it lost those English knowledges. So it didn't work well on the accent 200 hours data or the English accents that are available on those accent 200 hours of data. So when we are fine-tuning the model on EDEC data, it seems to mess up with general English knowledge. And yeah, and here our accent 200 hours data is very similar to like very standard English, like good audio records and lengths are also good, but EDEC test has some messy data, so their phonetic group is significantly different than the data available in accent 200 hours data.
You compare the difference of testing unseen and seen accents. How much does the performance drop when you test unseen accents?
Yes, we have. Yeah, so here was our zero-shot adaptation results. So our multi-teacher knowledge distillation improved performance for all the unseen accents. So compared to the fine-tuned one.
Yeah, but what's the difference between the seen and unseen accents? The main of the average performance on there.
Maybe here we can see that for seen accents, the relative improvement was 5.26%, but here the relative improvement was 10.18%. So,
but I meant the absolute error rate on seen and on unseen. So how much worse it is in unseen accents?
Not this particular test, but yeah, but just like this one, we have
maybe this roughly says that it's about 15% or 10% is the seen, and then 55 is the unseen. If you compare this first data set to any other data sets.
Okay, so
this Edinburgh data is unseen only, and this other data is foreseen accents.
So here we have the seen accent data. So the performance are much lower than the unseen ones. Yeah. But compared to the fine-tuned baseline, our method improved the performance on unseen accents.
Yeah, still.
But still we have some differences in seen and unseen data.
These are the seen accents. So there are kind of some Asian accents and no African accents.
No.
Did you have some Africans in the unseen?
I guess, yes.
Well, yeah.
Okay.
But that doesn't seem to stand out.
But comparing this one, so where the fine-tuned one is saved 58%.
Yeah, that's a big improvement. Yeah.
Over 10%, 10.5%.
And what's the don't know accent?
It's a mixed category, maybe.
Okay. That's one of the worst. Well, actually, Jamaican is the worst. But it still seems to be a hard problem, this unseen accent speech recognition. Even though you made quite a significant improvement there, but still, it's to be solved.
The gains are lower in countries with English as like official language. If you Southern British and Jamaican and Nigerian, and then the top one is like Italian.
Yeah.
Irish is the exception.
Is there any questions from Dayan or Anusha?
What's next for you? I'm considering a PhD. I'm not sure if Dan is still here and listening.
Yes, I'm here.
Yeah. Thanks for joining. So I'm considering a PhD. Maybe I will start immediately in Mikko's group.
Okay, that's great. Great to hear. And congratulations again.
Thank you.
Any other questions?
Yeah, I have a question. So in the beginning, you are selecting the wave to vector base model, which is trained only on English. And then you apply this technique of distilling teachers to make it like adapt to multiple accents. But did you have any results that actually the base model is, for example, the cross language? So like they was doing the first pre-training with like multiple languages. So maybe there might be some accents with that, like some information about that, and then just use that and train your stuff, and then see if it like how it compares with your only English, and then distill the accent, and then maybe already has the accent included, but only like training with English. Do you have any like which kind of method?
I guess I already messed up your question.
Yeah, I guess the question was that there exists a multilingual web-to-vector But you didn't choose to start from that, but you chose from
No.
English only.
Yeah, the English only.
And why did
Yes.
you?
So do you happen to have any maybe
So the main aim of this study was to showcase the capacity of multi-teacher knowledge distillation.
Yes, I know.
So we choose the simple web-to-vector baseline,
Yes.
and we then see whether multi-teacher knowledge distillation works or not. And it appeared that multi-teacher knowledge distillation works. Yeah, and it's better than standard fine-tuning.
Do you know about this English only web-to-vector tool? That does it have accented English as well there, or and how much of accented English and how much?
I
British English?
particularly didn't check the English data it was trained on, but in general, it should be like the case, American or British accented English dominant.
Yeah.
Because these data are mostly available.
Okay, if there are no more questions, I think let's thank Mehdi again and congratulate him.
Thank you, everyone. Thanks, Dan. Thanks, Anusha, for joining. Hopefully see you.
Congratulations.
Thanks.
It was a nice presentation.
Thanks. Bye. Bye,
Bye.
Dan.
Bye.